Jai Hind. Myself, Amita from AKGEC Training College, Ghaziabad. Now, in this video lecture, we will understand the amplitude modulation generation process and the reception process. In the previous lecture, we have learned how to solve the numericals based on amplitude modulation, what is modulation, and how the power has been calculated for the upper sideband and lower sidebands. So we have already understood that the amplitude modulated wave has basically three frequency components. First is the carrier power or the carrier frequency component, that is FC component. The carrier frequency component, three components, FC, the carrier, and FC plus SS and FC minus SS. So we have already calculated the power of the carrier wave PC, okay, and PC and PUSB and and the total power we are just revising, that was PC plus PLSB plus PUSB, and PT we have seen that 1 plus mu square by 2 into carrier power, right? So that all we understood about the power transmitted along with the amplitude modulated wave, what were the three components, and basically I told you to learn the basic formula of amplitude modulated wave, and that is nothing but S of AMT it is AC okay. So what we have done is that we have this was actually AM by AC, okay, and that was defined as, okay, this was the basic expression for amplitude modulated wave. Now coming to the amplitude modulated wave, which I told you how to get this standard expression, what are the system components or blocks which produce the amplitude modulated wave. Okay, so here we will see that first of all we are adding the two signals. First is my message signal and second one is my carrier signal, right? Message signal is empty and the carrier signal is simple sinusoidal signal, which I have taken as a carrier wave, and this carrier wave is being generated at the transmitter itself, and this carrier wave is of very high frequency to be generated because I want to modulate the amplitude of the carrier wave in accordance with my message signal. So first of all I will put this carrier wave and message signal to my adder circuit. Okay. First block is adder or summer block, in which I am adding my two signals. First is my message signal and second one is my carrier signal, that is MT plus AC cos 2 pi FCT. This will be my V1T. Now I am inputting this V1T into the square law device. Okay. Now how my square law device is working, whatever input we are giving to my square law device, it produces the output in this way. Okay. V1T to be multiplied with K1. Okay. V1T to be multiplied with K1 and V1 square T to be multiplied with some constant K2 and then it adds. That means the response of the square law device V2T is equal to K1 V1T plus K2 V1 square T, right? And this is the response of my square law device. Try to understand. So V1T is the input. This system square law device, what it does with my V1T is K1 V1T plus K2 V1 square T, right? So this is how V2T is being calculated. Now I will put this expression K1 MT plus AC cos 2 pi FCT V1T, K2 MT plus AC cos 2 pi FCT whole square. Now I will use the formula A plus B whole square and then I will do some modifications and we will get the result. Just apply this K1 M1T, K1 MT plus K1 AC cos 2 pi FCT plus K2 M square T A square plus K2 AC square cos square 2 pi FCT 2K2 MT AC cos 2 pi FCT. So how many terms I am getting this in this term? 1, 2, 3, 4, 5 and 6. 5 terms. Okay. 1, 2, 3, 4, 5. Okay. Now I would like to write this as here V2T, this V2T. This is cos square 2 pi FCT formula. So we can add it like this. For cos 2 theta formula if you want, otherwise you can leave it to. This V2T is K1 MT, K1 AC cos 2 pi FCT plus K2 M square T plus K2 AC square 2 cos square 2 pi FCT plus 2 K2 MT AC cos 2 pi FCT. This is a DC component. Okay. The band pass filter, it just allows only the frequency components carrier FC plus FF and FC minus FF. That's it. Okay. This will not be allowed by the band pass filter. Okay. This will be allowed by the band pass filter because it is passing C. It can only pass FC, FC plus FM, FC minus FM. Right? It is not going to allow this term also. Okay, because this is again a DC type of term, or you can say this is a very, low frequency term whose frequency is FM. Here it is, sorry, it is not DC. It is also of low frequency. Low frequency term, MT. This is 2 FC component, frequency is 2 FC. This is also not to be allowed by the filter, band pass filter. This empty and this multiplication, FM plus FC, it will give 2 components, FM plus FC and FC minus FM. So only this will be allowed. So these 2 components can only be allowed by the band pass filter. This will be rejected, this will be rejected, and this will be rejected. These 2 are rejected due to low frequency, and these 2 will be rejected because of twice of the FC. Because this band pass filter only is passing between the frequency range FC minus FM to FC plus FM. So this is the band pass filter which is passing only frequencies from FC minus FM to FC plus FM only. That's why only these terms will be allowed, otherwise all the terms will be blocked. So this is how we are generating the amplitude modulated wave. And after solving, we can get this 2k2 upon k1 empty. You will solve the expression and you will get this AM modulated wave in the same manner, right? The last term of the above equation represent the desired AM wave, and the first 3 terms of the above equation are unwanted. So with the band pass filter, which is allowing only 3 frequency components, FC, FC minus FM and FC plus FM, because the band is from FC minus FM to FC plus FM, and the output of the band pass filter will be containing only 3 components, and a square law modulator, that is AM generator, will give you the standard equation which we have already understood in the previous lecture. This is the standard equation of the amplitude modulated wave, and the AM generator is giving the same expression. So if you explain this in the examination, you need to make the block diagram, and then you will have to derive this output of summer, then output of the square law device, and then output of the band pass filter. All these 3 blocks, what they are working in the square law modulator, you need to explain the 3 blocks working for explaining the AM generation, and you have to get this final expression, right? At the transmitter, what we have done, we have modulated our carrier wave in accordance with the message signal, okay, in accordance with the modulating signal. Now I need to detect or demodulate the received amplitude modulated wave. That means now I want to demodulate the signal which already I have detected, okay. So at the receiver point, the transmitter part is over now. You have generated the AF, you have transmitted the AM. The transmitted AM has been received by the receiver. Now we need to detect or demodulate. Demodulation means to extract the message signal, from my amplitude modulated wave, which my antenna has recovered at the receiving point, okay. So this is how we will modulate the carrier wave in accordance with the modulating signal at the transmitter side. Now try to understand what we are going to do in this demodulation at the receiver end. We are talking now, this process is being performed at the receiver end. So here this demodulation is done at the receiver part, okay, right? So at the receiver we will apply the demodulated circuit, and from this AM modulated wave, which has been sent at some radio frequency range, and now I have to extract my original message signal. So The process of extracting the original message from the modulated wave is known as detection or demodulation. To perform the demodulation process, I have to employ one demodulator circuit at the receiver. Antenna will receive the signal and demodulator circuit will demodulate my signal. That means will extract the message signal from the received signal by the antenna, right? Now we have two types of demodulators which are required as per your course. You need to study these two modulators. First is square law demodulator and second one is envelope detector, right? So first of all, we will understand the working of this square law demodulator. This is my square law demodulator circuit. The first block is square law device, and then we will put one low pass filter. Why low pass filter? Because at the transmitter we have applied one band pass filter. Now here I have to receive, I have to extract the very low frequency component, which was originally my message signal. So that's why I will employ a low pass filter at the demodulator circuit or at the receiver end. So square law demodulator is being used by the receiver circuit to extract the original signal. The standard AM wave has been received, which is already I told you that is AC 1 plus Ka and T cos 2 pi FCT, where Ka is nothing but the modulation index, that is AM by AC. Okay. So AM by AC already we have calculated. Somewhere it is written as Ka, somewhere it is written as mu, no worries at all. This Ka into MT, if you are not known that MT is only a sinusoidal function, you can use this expression too. What this square law device will do? This square law device, whatever V1T I am giving, V2T is K1 V1T plus K2 V1 square T. Okay. So K1 V1T, this I will multiply this equation to K1. I will square this equation and will just solve this expression K2 V1 square T. After solving, putting the V1T value into the equation number, this is equation number 1, suppose this to be equation number 2. So this put the value of equation number 1 in equation number 2 and solve the expression. Here you will find how many terms? 1, 2, 3, 4, 5, 6, 7 and 8. Now this V2T is being passed to LPF, low pass filter, right? This is a very simple expression you can solve on your own. Try to understand what this low pass filter is doing. The low pass filter is only tuned to FC. Okay, it is only tuned to FC signal. Oh, sorry, FM signal. Because FC is already high, it cannot receive the FC signal. It is only tuned to the FM, the low frequency range FM. Okay. Now see the terms very carefully and decide which terms will be neglected by the low pass filter and which terms will be passed by the low pass filter at the demodulated output terminal. Okay. Look at the first term. This is centered around FC. FC is high. Low pass filter won't pass it. It will get, right? Okay, coming to the next one. This frequency is 2 FC. Low pass filter is only tuned to FM. It is not going to pass this also. This is DC. Low pass filter won't pass it. So this is also cut. This is 4FC. No, low pass filter has no capability to pass it. It will reject this. This is also M square T. M square T means some signal of double frequency range, 2 FM. So it will also be neglected by the low pass filter, because low pass filter is only tuned to FM only. So it won't pass twice of FM, right? Again here, 4FC component, it is not going to be passed by the low pass filter. Here again, this 4FC component, it is not being passed by the low pass filter. Only this term, only empty is coming with some constant value. It will be only passed by the low pass filter, and low pass filter will allow this term only at the output, that is K2 AC square KA. And this is the only term which will be passed by the square law demodulator circuit. So this is how we are going to receive the amplitude modulated wave, right? So square law demodulator contains two blocks. First of all, square law device, and then the low pass filter, right? So all these terms, as we can see, this square law device K1 AC cos 2 pi FCT, this term won't pass because it is of 2 FC frequency component. This will also 2 FC. This is beyond the capability of the low pass filter. It won't be passed. This is a DC component. Similarly, this is 4 FC component. This is M square T. This won't be passed by the low pass filter. This is 4 FC component. This is 4 FC component. Only this particular frequency term will be passed by the low pass filter, and the demodulated output would be K2 AC square KA MK, right? Now the second demodulator circuit is the envelope detector. This is a very simple type of demodulator. Again, this detection, this AM detection is being performed at the receiver end, right? What we have received? We have received the amplitude modulated wave. So just it employs this amplitude modulated wave is being applied to the, the input of the envelope detector. We have put one diode. You are very well aware of this capacitor and this resistor. Okay, this is the envelope detector for amplitude demodulation. The output MT, this is the amplitude C. Here at the input side, we are giving the amplitude modulated wave, and we are converting it to the output MT. So since it is an envelope detector, first of all, you need to learn this particular circuit. This employs only 3 components: the diode, the capacitor, and the resistance. Okay. The AM broadcast radios, the performance of this particular circuit is good, but it is not at the required standard. So we can also use some other demodulated circuit, but you need to understand this particular circuit as envelope detector. So here what it is doing, see, the envelope of this amplitude amplitude modulated wave, this is the envelope, right? Okay, now this is being detected by the diode circuit. The diode will either get forward bias or it will get reverse bias. When it gets forward bias, the capacitor will get charged, and the voltage, whatever voltage appears, it will come across the resistance, and the envelope will be appearing across this resistance, and you will get the output like this, empty. The envelope of the empty will be detected and the capacitor will charge at the same value of the envelope of the amplitude modulated wave. And you have to make this circuit, and here you have to explain for the demodulator circuit. Kindly note these two circuits you have to remember, the square law demodulator circuit and the envelope detector as demodulation. So for this square law demodulator, you have to explain like this, the output of this square law device, and here you have to explain the working of the capacitor and how the resistance is giving you the voltage just equal to the envelope of the MT, and this will depend totally on the diode on and off conditions, right? So we have seen the AM generation and AM detection. That's all. Thank you.